So folks, in the last video I showed you how to upload this script into CalcPlot 3D. So now that we've got it uploaded into CalcPlot 3D, let's start exploring it. So the first thing that you'll notice over here is that I've given a vector valued function. So in CalcPlot 3D we don't call it a vector valued function, instead CalcPlot 3D calls it a space curve. You can see here it's labeled as R of t. But that outputs the same thing that our vector valued function would output, and here we have the three parametric equations describing this curve. Notice that this t cosine t, t sine t sort of resembles a circle in a given plane. So for a fixed z value, if you fixed a z value and allowed t to vary, you'd have some circle in the plane, but the radius of that circle is changing because of that component of time right here. So we can see here that we have these concentric circles, but the radius of those circles is changing as time is changing in these problems. You can see that time is set up to go from -10 to 10, and you can adjust that, but I felt this was a good viewing window. The next thing I want everyone to do is just slide this slider along and kind of see what's happening here. So pause the video and just take a few minutes to just sort of play around with this and see what's going on here, and then we'll talk about it more. So before we get into what each of these components means, and I want to discuss them further, let's go ahead and put a couple more components on here. So we can see down here in this graph, we can see that as we move along the curve, I've got these three vectors. I've got this purple vector, this blue vector right here, and this red vector right here. And I want to discuss each of those separately. We'll talk about what they mean. Before we do that, I want to show you a couple other things we can do here. If we click on Settings, we can go ahead and turn on something called the Oscillating Plane. That's something that we're going to look at as we go through this video. So you can see now I'm moving that and I've got this oscillating plane going. Notice that the oscillating plane appears to have two vectors lying within it, the purple one and the blue one, and one vector that's normal to it. That red vector there is normal to that oscillating plane, and we want to talk about that. The next thing you can see is that if you click on Settings, and go ahead and, after I do this, pause the video and do so, if you click on Settings, you can see that I have asked it to sketch the oscillating circle, and that oscillating circle is this black circle that you can see right here, whose radius is changing as this curve is changing. Now we're going to talk more about that, but one thing I want you to think about, that radius of that oscillating circle, is it's related to this k value up here. This k value is computing what's called the curvature of this curve as we move along it. So again, folks, I'm not explaining what these are right now, but I'm wanting you to think about this. Notice that as my curvature gets smaller, the radius of the oscillating circle gets larger. Likewise, as my curvature gets larger, there it is at 0.6, the radius of my oscillating circle gets smaller. And notice about here, the curvature is about as big as it gets, and that's where the radius of that oscillating circle is the smallest. So again, folks, pause the video and play around with that, and then we'll get back to it. So now that you've done that, I'd like to go through and start taking away some of these components. So let's just get down to the point where we just see the original function, the vector valued function, and the curve that's sketched by it. So I'm going to click on Settings here, and I'm going to go ahead and turn off the oscillating circle, and I'm going to turn off all of these vectors here. So I'll turn off the oscillating plane that's formed by the unit tangent and unit normal vectors, so I'm turning those off, and I'll also turn off the unit by normal vector. At this point, if we look at this curve, this is what we studied initially when before we did any calculus and we just talked about a vector valued function. At any point in time, we plug that time value into the three component functions. That outputs a new vector. The new vector is sketched in blue, and the tip of that new vector is the point that we consider being along the curve, and there we have this situation here. So we already know what R of t is. This is R of t. And what have we learned how to do? Well, we've learned how to do calculus on these vector valued functions, and we know how to take the derivative of this function R of t. So this is our displacement vector, R of t, and we've learned how to compute its derivative, which we call R prime of t, and we do that component-wise. Remember that the derivative vector valued function only has an intuitive meaning in terms of tangents if the magnitude, or if the derivative is not the zero vector there. So as long as when you take r prime of t and compute it, you don't get the zero vector, then we can call the derivative of it a tangent vector. So let's go ahead and put on the tangent vector here. So I'm going to click on Settings, and I'm going to say Show the Velocity Vector. Okay. So here we have the velocity vector, and this is nothing new, folks, where this blue vector corresponds to the position at a point, and then as long as r prime of t isn't 0, which isn't in this case because it's not the zero vector, then we can call this black output vector, we can call it the tangent vector, and we get that by computing r prime of t. So we can see here, we can see that the velocity of this curve changes as we move through here. Here it has a very small velocity because the magnitude of that black vector is small. And here it's increasing, the magnitude anyway of the velocity vector is increasing. And always as we're going through this, not only is the magnitude of that black vector changing, but of course so is the direction of that black vector. So again, for any vector valued function whose component functions are differentiable, we can compute r prime of t. As long as r prime of t isn't 0, then we call that output vector r prime of t, we call it the tangent vector. But here's the situation, folks. We've already been exploring different ways of parameterizing curves, and we know that different parameterizations will yield different tangent vectors. So the tangent vector is dependent upon the choice of parameterization. Now, when I say that, what I mean is the magnitude of the tangent vector depends on the choice of parameterization. So the length of that black vector might be different if I had a different parameterization of this curve. However, while the magnitude of the tangent vector depends on the choice of parameterization, the direction of this black vector does not. Meaning if somebody else had a different parameterization of the curve here, this black vector at this point might have a different length. It might be longer, it may be shorter in magnitude, but the direction will still be the same. So because the magnitude of the tangent vectors depends on the choice of parameterization, but the direction does not, sometimes for standardization, all we do is we look at the direction of those tangent vectors. So how do we take a vector and just consider its direction? Well, we make it a unit vector. That is, we're going to take whatever this black vector is and divide it by its length. And when we do that, we have our unit tangent vector. So folks, as a reminder, this is how we compute the unit tangent vector, which we label as t. We take the derivative of our position vector. That's just that velocity vector, right? That's that black velocity vector right here, but then we divide that black velocity vector by its magnitude. Remember, that's just a scalar because it's magnitude, so that's a scalar, so we divide each of the components of r prime of t by the length, forcing this to be unit. So now let me go ahead and put t on this graph. So I'll go here and click on Settings, and I'll say Show the Unit Tangent Vector. Okay? Before I click that, folks, imagine where that unit tangent vector should be. So think about that. So here I've turned on the unit tangent vector, and unfortunately I don't have a lot of control over the colors that CalcPlot3D uses. So here I've got this purple unit tangent vector. Notice that it is pointing in the same direction as the black velocity vector, but unlike the black velocity vector, whose magnitude is always changing, the magnitude of that purple unit tangent vector does not change, and in fact it is unit because of the way we constructed it. Because we divided it by its magnitude, the magnitude of this vector here, called the unit tangent vector, it does have magnitude 1. So that's our unit tangent vector right here. So folks, now we've discussed the unit tangent vector, and we get it by taking whatever velocity vector we have, depending upon our parameterization, and then normalizing it. So at this point, there's no need to consider the velocity vector anymore, so go ahead and turn off the velocity vector. Now, this unit tangent vector tells us the direction in which the curve is traveling. It no longer tells us the speed at which the object is traveling because we divided out the speed when we made it unit. But notice that this tangent vector, the curve is not going to proceed in that direction for all time. As time continues, this curve is not going to head in the direction of this tangent vector. Instead, this tangent vector, which is pointing the direction we're traveling, is going to change. And that's what we want to learn how to measure next. How is this unit tangent vector changing as we move along? So I'm not asking how is the position vector changing anymore. The position vector is changing. We've encapsulated that information as much as we needed. But now we're going to ask the question, how is this purple tangent vector changing? So before we get into the principal unit normal vector, which is our goal of this next part, we need to talk about the word curvature. Curvature tells us the rate at which the curve is changing. It tells us how fast the curve is changing. Notice that the curvature, which is computed up here, is a scalar value. I'm not going to go into curvature in this video because you're going to be exploring that in your My Math Lab for this section, your pre-work for the My Math Lab. But I do want to point out that the curvature is a scalar value that in a sense measures the tightness or curviness of a curve. And you can see that as I move through here, there's the curvature values. Watch them change in comparison to the curve itself. And notice that where the curve is changing direction most rapidly, that's where the curvature takes on the greatest value. And notice as it gets further out, notice that say for right around here, although the curve is changing position quickly, it is not changing direction all that quickly, and so the curvature k is a small number. And in fact, if we were to zoom out a little bit, notice that the curve begins to resemble something of a straight line, and as I move out farther, my curvature gets closer and closer to 0 because the curvature of a straight line, the curviness of it, is measured to be 0. So take a second to explore that curvature number. So folks, if we take this unit tangent vector and we want to talk about how it's changing, notice if I advance time just a little bit. So I'm going to advance time by 1/10 of a second here. So when I hit enter, this purple unit tangent vector is going to move when I hit enter. There it is. So we could look at the difference between where the vector was and where it ended up over a small increment of time. And so we have its derivative vector. We've got the derivative of the unit tangent vector that we could discuss. That derivative will be a new vector, and that new vector will have both magnitude and direction. The magnitude of the change in those vectors is what's captured by curvature. The direction of that change is going to be what we call the principal unit normal vector. That's what we want to compute next. So here we have our formula, per se, for the principal unit normal vector. The way I want you to think about it is don't think about this as a formula to memorize. We've got the unit tangent vector and we want to ask how is t changing, but we only want to ask the direction, how is the direction of t changing with time. So if we just took dt as we have in the numerator, we would have that change in this blue unit tangent vector with respect to an increment of time. That new resulting vector has both magnitude and direction, but the magnitude of it corresponds to that curvature value there. And so we don't want that curvature value, so one way to account for that is we're going to divide it again by its length, forcing the derivative to be unit, and we call that the principal unit normal vector. Folks, a quick comment on the name principal unit normal vector. We have several normal vectors. We've seen the word normal show many times in this class, and so for clarification, we will often use the phrase principal unit normal vector to make sure that you know which normal vector we're talking about. When it's clear from context, or sometimes just because I'm lazy, I may just call this the normal vector, but I really should be calling it the principal unit normal vector. So returning to this example, if I put time back where it was at -8.2, there we've got the unit tangent vector, and then if we advance time forward just a little bit, we've got a new vector, and the difference between those in limit is essentially what we're looking for as the change in time goes to 0. That's what we're looking for when we want this, this new vector, and then we're going to only focus on its direction. And so if we compute that derivative, this is what we have here, and let me go ahead and ask CalcPlot3D to plot that. So here is the principal unit normal vector. So the first thing I want to show to you folks is that if I advance time a little bit further, something's going to be much more clear here. So let's put time to say right about here. Here you can see that this blue vector, and unfortunately both of these are blue in CalcPlot 3D, this lighter blue vector is my principal unit normal vector. It is not necessarily pointing in the same direction as my position vector. So in some circumstances it may look like that's what's happening, but that's probably unique to the curve itself that we're studying. Or it might be, dependent upon your point of view as you're looking at this. So there's our principal unit normal vector, and it is pointing in the direction in which t is changing. So if I were to advance time forward just a little bit, this purple unit tangent vector will change, and its direction component is going to change in the same direction as this principal unit normal vector. So let me advance time forward by just maybe 1/100th of a second, so we have 2.81, advancing it forward just ever so slightly. I don't know if you could see that move. Let's make that a little bit more drastic. So let's advance it forward even more drastically so that you can see that the direction of this vector, it moved inwards the same way that this principal unit normal vector is pointing. Folks, I do think it takes some time to understand the principal unit normal vector. I'm not asking you for you to master this right now. So instead, let me give you a great visualization for what the principal unit normal vector is doing. If we come back here to our settings, we can go ahead and return on the oscillating circle. And what I want you to notice about this is that something I said before is that the size of the unit circle, which is dictated by its radius, is always inversely proportional to the curvature. So as the curvature gets closer to 0, the size of this oscillating circle in radius approaches infinity. So the bigger the curvature, like down here we've got a big curvature value, the smaller the radius of the oscillating circle. That's something I've already said. But the thing I want to point out here is notice that my principal unit normal vector always points towards the center of that oscillating circle. And so I think a very handy interpretation of the principal unit normal vector, until we get more comfortable with it, is that if I were to want to put a circle that approximates my curve at a point, notice I'm not talking about putting a tangent line that approximates my curve at a point. Instead, I'm putting a circle, I'm fitting a circle to this purple curve that approximates the curve at that point, that the principal unit normal vector, this light blue vector here that we're learning how to compute through this computation here, always points in the direction of the center of that circle of curvature, or that oscillating circle as it's called. Okay, so now we're ready to introduce actually the very last component here. And that's because once I've got two vectors, I can always construct a plane in which those two vectors live. And so that plane is called the oscillating plane. Let me go ahead and ask CalcPlot 3D to put that oscillating plane back in. We've already looked at it, but there it is. There's that oscillating plane, and we see, yep, sure enough, that, let me come up about here where it's easier to see. Sure enough, this plane is the plane that's formed by these two vectors. Okay. By the way, it's also worth noting that these two vectors are always orthogonal to one another. That is not a coincidence, that's by construction, and we'll talk more about that in class. But once I've put this oscillating plane up here, we've got something that we're ready to talk about, and that is every plane has a normal vector. Now careful folks, this is different than the word principal unit normal vector, which is referring to this blue vector right here. This beige looking plane that we can see here, let me go ahead and turn off the oscillating circle. This beige looking plane that we can see here, it itself has its own normal vector, and I'm going to ask CalcPlot 3D to plot that. There is its own normal vector shown in red here. And so this red normal vector is called the unit binormal vector. Okay. But notice that it is just simply a normal vector to this oscillating plane. The other thing to notice is that you determine, remember, normal vectors to planes can point in one of two directions. This one is always following the right-hand rule where I take t crossed with n, and that will give me this red vector b here. So we use the right-hand rule to figure out the direction in which the unit binormal vector is changing. Okay? So folks, this is a little bit confusing. The principal unit normal vector is one of the two vectors lying in the osculating plane. That osculating plane has its own normal vector, which we call the binormal vector. So I'm sorry, we're sort of at normal alphabet soup here. It will take you a little while to keep track of those components. So folks, the final thing I want to show you is torsion. And if we look at this, I'm going to ask this to display the whole TNB frame. So here you can see the entire TNB frame has been displayed. Let's move it to where it's a little easier to see the components, maybe right here. So here we can see, here's our unit tangent vector, which is always pointing in the direction of motion. The unit normal vector, which is always pointing in the direction which the curve is turning. And those two form this lower plane right here called the oscillating plane. And then we've got the oscillating plane's normal vector called the binormal vector, pointing, always following the right-hand rule. This creates what we call the TNB frame. And notice up here, all three of those vectors are being given for you up here, and we can slide this along. Okay. Now, we don't use much of this in a math class, but in a physics class, what you would use is you would use this TNB frame as a sort of moving coordinate system. That is, if you want to talk about forces acting on this object, or if you want to talk about the object's velocity and acceleration and whatnot, a lot of times it's easier to use coordinates in terms of these three reference coordinates, t, n, and b, as opposed to the reference coordinates we usually use, I hat, j hat, and k hat. So rather than using I, j, k to describe your vectors, you use t, n, b, and you build this moving three-dimensional coordinate system that moves along the curve. That's the essence, that's the purpose of studying this TNB frame. We will not be doing a whole lot of that in this course. So the final thing I want to show you though, and I constructed this example decently carefully. There's actually a rounding that's happening here. This is not actually the number 1 k hat. It's something like 0.0009 k hat. So it's not exactly 1 k hat, but up to the machine's rounding, it looks like 1 k hat. I want us to pay attention to this vector b here. So vector b currently is pointing basically straight up. It's basically just the 1 k hat. So if I were to put that vector right here, it would only be pointing in the z direction with a unit of 1. Okay? So I want you to see how this vector b, notice as I'm moving along this oscillating plane for around here, the vector b is not really changing. And we also see that as vector b is not really changing, that essentially this curve is lying inside of the same plane, pretty doggone close to staying in the xy plane. Now it's actually not truly in the xy plane. It is moving out of it slightly as I do this. Again, that's up to the machine's rounding, but it's basically staying in the xy plane. So even though the vectors n and t are changing as I move these, and you can see the values of vectors n and t changing, the vector b is basically staying the same here. Now what's interesting is as I get to another part of this curve, let's look at those values for vector b. All of a sudden, once I get to here, notice the values for vector b changes. For instance, right here, b is certainly not just pointing in the k hat direction, and you can see it's got all three of the components showing up here. And as I move further along, that becomes even more drastic. Here b is not pointing in the k hat direction any longer, and in fact we can see the values of b changing as we move through this twisty part of the curve. And this is actually why I built this example, because I wanted you to see, notice that down here the osculating plane is basically staying in the xy plane. The osculating plane, this lower one, is not changing as time changes by very much. Actually, it's changing slightly, but this osculating plane is basically, if I were to look in the look kind of along here, that osculating plane is not really changing out of the xy plane here. But look what happens around here, right when I get to about here, that osculating plane starts twisting. Now, how the osculating plane is twisting, that's the one, in fact, let me take off the, let me take off a little bit here, folks. So I'm going to take off the whole TNB frame, but I'll ask it to show these three vectors and to label them. and then let's just put in the oscillating plane here. So I've just got that oscillating plane here. So what we can see is that this oscillating plane is moving here. It's very much in the XY plane until we get to about here, and notice the oscillating plane is twisting around. So the last component we have to talk about, and this has been a long buildup, is the notion of torsion. And torsion is asking the question, how is the oscillating plane itself changing? Notice the oscillating plane, although the vectors t and n are changing, the plane itself is staying in the xy plane here. And we see that because the vector b is not changing. But once the vector b starts changing, we also get a twisting effect in the oscillating plane. So, putting up the values of the TNB equations here, notice that b now, whereas it wasn't really changing with respect to time down here, although there was a very minor change, b is now changing up here with respect to time. And essentially, asking how the direction of b is changing with time, and this is an oversimplification, is what we mean by torsion. So notice that down here, although the plane is moving and t and n are changing, you can see that happening down here, b is not changing. And so down here, the torsion is essentially zero. There is no twisting of that oscillating plane. But as we move over to here, we're going to start generating, there's torsion now in this curve, and we see that reflected in the fact that our vector b, the binomial vector, is changing. So that's a gross oversimplification of what torsion is, but we're basically giving a way of quantifying to what degree is this vector b changing as time moves on. So folks, pause the video, spend some more time exploring this, and this is what we're going to be discussing in class. So folks, if you felt confused by this video, no worries. I recommend maybe you should watch it twice, maybe even 3 times before coming to class, and that way you feel real comfortable with the intuition for what we're doing. Because in class, we're going to start computing stuff. But when we start to compute stuff, we might lose track of the intuition. And so do spend some time prior to class developing this intuition. Thanks for your patience. I know this was a long video, but I'll see you in the next one.